Yeah, good evening, AP Physics students. Mr. Gerson coming at you here, talking a little thermodynamics today. Got a good problem measured up for you here. So let me grab my pen here and we'll get going. All right, here we go. Oh my goodness. Oh, I went to grab my pen and all of my paper clips. Oh, they fell. Oh, they fell over. Oh, shoot. And I had this great problem set up. Wouldn't it be great if all of these paper clips, just in and of themselves, all their on their own, organized themselves and put themselves back in my paper clip container? Wouldn't that be great? Well, as it happens, we all know that things do not organize themselves, spontaneously anyway. As it turns out, the way the universe works is things naturally go from an ordered state to a disordered state. So, shoot, I'm going to have to do some work here and organize these paper clips back together. Well, enough about my troubles there. Let's talk about entropy. Oh, hey, how about that? Entropy is a measure of the disorder of a system. And just how we know that my paper clips are not going to spontaneously by themselves organize themselves. The second law of thermodynamics states that the disorder of the universe or any closed system is always increasing. And in thermodynamics, we have a special way of defining entropy or disorder. By itself, heat always flows from hot objects to cold objects. And as this happens, the system gets less organized, less ordered. And we say that the change in entropy or change in orderliness of a system is defined to be the heat transfer divided by the temperature. So the units for change in entropy are joules per Kelvin. So note that in this definition, we can only calculate changes in entropy. So much like potential energy, we can't calculate an absolute value of things or measure the absolute values of potential energies. We can only calculate changes in potential energies. And likewise, changes in entropy. Okay, let's do a little example problem now that we know about entropy. So problem 39 states that I have an object, a box of mass m, and it is traveling at a speed v. And the mass of the box is 10 kilograms. And the initial speed of the box is 3.0 meters per second. And the box slides and it comes to rest due to friction. Now, this box happens in a room just like maybe our physics room. So it's at room temperature or 20 Celsius. Or the book says in this problem that this process happens at 293 Kelvin. And then it wants to know what is the change in entropy of this system. Okay? So whenever you're talking about entropy, you got to be talking about some type of heat transfer. So in this problem, as the box loses kinetic energy, that kinetic energy is going to get transformed into heat. For instance, if we measured the temperature of the two surfaces here after it slowed to a stop, that temperature might be just slightly larger. Okay? So to calculate the heat transfer here, I'm going to find the change in kinetic energy here. So that would be 1 half m v sub f squared minus 1 half m v sub I squared. Okay, so this is equal to, well, the final kinetic energy is 0. 1 half of 10 times 3 squared would be the kinetic energy here would decrease by 45 joules, which means that is also equal to plus 45 would be the heat gained by the floor in the box. So if we were to then use that to calculate the change in entropy, it would be 45 joules divided by 293 Kelvin. And if we work that out, we'd get about 0.15 joules per Kelvin would be the change in entropy of this system. All right. Well, nice work, physics students. Really cool article today in the Sunday paper here. As it turns out, spiral galaxies, which I'm sure you're all familiar with, like our Milky Way, have arms in them, right? These little arms, these swirls, okay? And as it turns out, this swirling is a permanent feature of these galaxies. You might think, like, when you run a canoe paddle through the water, you get a swirl for a little bit, but the swirl eventually goes away. It turns out researchers at Wisconsin-Madison and Harvard got together and did some complicated computer simulations of galaxy evolution and showed that those swirls actually stay. They're not just temporary. So I'll bring this article into school tomorrow. If you're interested, stop by and check it out. All right, nice work, physics students. We'll see you tomorrow.